Greetings, Panthers. It is Dr. Augustine. I hope you're doing well today. Today we're going to take a look at the ideal gas law, and this video is going to cover chapter 6.4 intro, cleverly named the ideal gas law. And what we're going to do is we're going to start by combining the three simple gas laws that we already saw in the prior two videos. Remember, if you recall, those were called Charles's law, Boyle's law, Charles's law, and Avogadro's law. So I'm going to show you how by simply combining those, we get a new equation which we call the ideal gas equation. You might be familiar with this, PV equals nRT, but I'll describe where that comes from. Then we're going to briefly talk what is an ideal gas. What do we mean by that term, ideal gas? We're going to find out what R is, or I'm just going to tell you what R is. And then we're going to define a new term that we call the molar volume at standard temperature and pressure conditions. We'll do a couple of ideal gas type equations, and then we'll introduce this idea of molar volume. So let's get started. Recall that we had three different relationships. We had Boyle's law, which we said that the volume is inversely proportional to the pressure. This was Boyle's law. We had Charles's law, which said that the volume is directly proportional to temperature. And if you remember our examples we gave, Boyle's law is if you're squeezing a balloon, the more pressure you put on the balloon, the smaller the volume gets. They're inversely proportional. Charles's law, we said if you leave a balloon in your car and it's cold at night, you will find out that the next morning it will have shrunk down. The colder it gets, the smaller the volume gets. And then the last one we had is that the volume is directly proportional to the number of moles. This is Avogadro's law. That one in itself is not that surprising. What is surprising is it does not matter the type of gas that you have. If you have the same number of moles, you have the exact same volume. That's kind of, I think, the interesting result from Avogadro's law. So what we can do is we can combine all three of these equations into one. And I've written a proportional sign for each of these. So I could say the volume is proportional to number of moles, temperature, divided by pressure. Okay, what I've done is I've just combined those three different simple gas laws, which we already gave some example experiments for, combine them into one equation, and we have a proportionality symbol, which means, as the temperature goes up, the volume goes up. As the number of moles goes up, the volume goes up. As the pressure goes up, the volume goes down. That's what this proportional sign means. But if we want to change that to a math equation, we want to change that to an equal sign, I need to put in some sort of proportionality constant. And I'm going to use the variable R for this. And we could have chosen any variable name, but R has a special name in this world, and this is called the ideal gas constant. So that equation is V is equal to RNT over P. Now that we've put a proportionality constant in there, we usually rearrange this so we bring the P over to the V side of the equation and we say PV equals nRT. This is called the ideal gas equation. And it's a very common equation, one my wife remembers from way back when she took general chemistry. And you can see actually that under a certain set of conditions, for example, in Boyle's law, under constant number of moles and constant temperature, we get back Boyle's law from PV equals nRT. If we leave this in this form, V equals nRT over P, if we have a constant number of moles and a constant T, then we have V equals R over P. If we have constant number of moles and constant pressure, we basically get back Charles's law. Constant number of moles and constant pressure, we have V is directly proportional to T, and we get Avogadro's law under the conditions of constant temperature and pressure. So those go away, and we have V is directly proportional to N. So you can see from the ideal gas equation, we could have derived Charles's, Boyle's, and Avogadro's law. We went the opposite direction because that was the way the historical discoveries were made, but you get back the simple gas laws from PV equals nRT. So in other words, this is sort of the guiding equation for understanding reactions of gases. So our next question we want to ask is, well, what exactly is an ideal gas? Why do we use this term ideal gases? So an ideal gas is basically a gas which obeys the ideal gas equation. And that's not a super satisfying answer. Let me make a couple of points about it. First, there's no such thing as an ideal gas. So that's always disconcerting to students to say, well, you're teaching us about this thing called the ideal gas equation, and then you tell us there's no such thing as an ideal gas. So an ideal gas perfectly follows this equation. And it turns out that there's some assumptions that we make about the ideal gas, one of which is that the gas molecules do not interact with each other. Okay, that's an assumption that we make. And it turns out that is not true, and the reason why it's not true is gas molecules have electrons and protons, and oppositely charged things like to interact with each other. Opposites attract. So in the real world, the electrons from one gas molecule will feel the protons of the other gas molecule. Likewise, they'll feel the electrons and get repelled. And the protons from one will feel the electrons of the other. So in the real world, gas molecules do have attractive and repulsive forces. We are going to make the assumption, though, for an ideal gas that they don't. Now, again, you may be asking yourself, well, okay, why are we doing this then? Why are we even talking about this? The reason is because at reasonable conditions, meaning conditions under which things act or behave as a gas, like normal pressures and normal temperatures. When I say normal, I mean like 1 atmosphere of pressure or room temperature or something sort of reasonably close to that. Under normal conditions, real gases behave like ideal gas. In other words, we can ignore these interactions between the gas molecules under quote-unquote normal conditions. Okay, we're going to do a problem here in a minute. Let's just make the assumption then, if you have something that's a gas under normal-ish laboratory conditions, we are going to assume that the gas molecules don't interact with each other, and we're also going to assume it behaves according to the ideal gas equation. Now, let's assign one other number here. Let's say, what the heck is this R? What is the value of that R? So it turns out R is equal to 0.08206, and some weird units on this: liter atmosphere per Kelvin mole. Okay, these units are really important. They're actually going to define how the rest of the calculations that you do go. Let me simplify this just a little bit. Usually, most calculations, 0.0821 liter atmospheres per Kelvin mole is sufficient. Okay, so this is a number you either need to memorize or will be given to you on a test, but this is called the ideal gas constant, and that's the value of it. All right, so here's these are not trick problems. I think most of the equations in this chapter are quite straightforward. If you know PV equals nRT, you can do an awful lot of the type problems that you'll see, but the trick is you have to put the units of the other variables, volume, number of moles, and T, you have to put them in liters, you have to put the pressure in atmosphere, you have to put the temperature in Kelvin, and obviously the moles are going to be in moles. Okay? So, not all problems start out with the variables in those units. For instance, in lab, a lot of the measurements you might make, the volume measurements are often in milliliters. Okay, so that's going to need to get converted to liters. The pressure is often in millimeters of mercury, torr, etc. That needs to be converted to atmospheres. And the temperature is usually in degrees C, and that's going to need to get converted into Kelvin. Okay? Other than that, the problems are very straightforward. You just need to make sure that you put these pressure, temperature, volume into the units, which will allow the ideal gas constant to cross them out. Now, there are other ideal gas constants with other units which cross out, let's say, degrees C, or cross out millimeters of mercury. We don't, in this class, in my class, we don't worry about that. This is the only one we worry about, but that does mean you need to convert these into the correct units. All right, so let's take a look at two different types of problems. One is a very straightforward problem, and then the other one is one I call changing conditions problems. So let's take a look at those two problems. All right, so here's our first example problem. Calculate how many moles of nitrogen are in a 125 milliliter flask if the pressure is 755 millimeters of mercury and the temperature is 20 degrees C. This is a really straightforward problem. All we need to do is we need to identify what all the variables are. So we're going to say pressure is equal to 755 millimeters of mercury. Temperature is equal to 20 degrees C. Number of moles, that's the thing we're looking for, and the volume is equal to 125 milliliters. All right, so I'm going to solve this equation for number of moles. So N is equal to PV over RT. And if we recall, R is equal to 0.0821 liter atmosphere per Kelvin mole. I would not call this a trick problem, but we do need to remember each of these units then needs to be consistent with R. So volume is going to need to be converted into liters, pressure is going to need to be converted into atmospheres, and temperature is going to need to be converted into Kelvin. And I'm seeing that this should be millimeters of mercury. All right, so let's just do that one at a time. Let's take the temperature. We're going to convert this into Kelvin. So this is 20 degrees C plus 273 is going to equal to 293 Kelvin. The volume is 125 milliliters times 1 liter for every 1,000 milliliters. Milliliters cancels milliliters. So that's going to equal 0.125 liters. And the pressure is 755 millimeters of mercury times 1 atmosphere per every 760 millimeters of mercury. That's going to cancel that, and that is going to equal to 0.993 atmospheres. So into my original equation, I plug all these new variables or numbers, 0.993 atmospheres. Volume is 0.125 liters. R is 0.0821 liter atmosphere per Kelvin mole, and temperature is 293 Kelvin. Make sure our units cross. Atmosphere cancels atmosphere, liters cancels liters, Kelvin cancels Kelvin, and we're going to have 1 divided by 1 over mole, which will give me an answer in moles. So this is going to equal to 5.12 times 10 to the minus 3 moles of nitrogen. Okay? So this first problem, a very straightforward, simple problem. The only, if you want to call it a trick, is you got to make sure that the units of your pressure, your temperature, your number of moles, and your volume are consistent with the ideal gas constant. As long as you do that, it's very straightforward, and then it's just a plug-in. Make sure you have the significant figures right. Make sure you have the right scientific notation, and you're good. All right, the second problem we're going to look at is a classic type problem with ideal gas type reactions, and I call these changing condition problems. I don't think any books call them this, but I like to refer to these as changing condition problems. These are very typical for ideal gas type things. So if you take a look at this, look at the wording, and you'll see what type of problems I'm talking about. You have a sample of gas in a 12.5 milliliter container. The pressure of the gas is 785 millimeters of mercury at room temperature, 22 degrees C. If you hold the container in your hand so the temperature rises to 37 degrees C, what is the new pressure? So what you notice is you have some starting conditions. Okay, you have starting volume, you have a starting pressure, you have a starting temperature, and then you do something to it. You heat it up, you expand the container, you add gas to it, you change the pressure, and then you want to find out what happens to some other variable. So these are what I call changing condition problems. You have some initial conditions, and you go to some final conditions, and you're trying to find out what happens to that gas. So here's the key to solving this type of problem. And once you understand this, you're going to see these are all pretty straightforward. So I'm going to say P initial, V initial is equal to N initial, R, and T. So R does not change no matter what is happening. Now, in this particular case, we're looking for new pressure, but we could do this for any of these variables. Okay, so if I solve this for R, P initial, V initial over N initial, T initial is equal to R. So what that's saying is, under these starting conditions, these initial conditions, that's all equal to R. Well, what about the final conditions? That would be like P final, V final is equal to N final, R times T final. And if we do the same thing where we solve for R, P final V final over N final T final is also equal to R. So if you notice, the initial conditions are equal to the final conditions through R. Since R never changes, we can set these two equations, this equation and this equation, we can set those equal to each other. So let's do that. P initial, V initial over N initial, T initial is equal to P final, V final over N final, T final. Now, I would not encourage you to try memorizing this equation, these three different equations. I would encourage you to memorize PV equals nRT and then just recognize, because R is always the same, I can set these two equal to each other. So this actually really makes this problem very straightforward then. We just have to go through and identify what are the initial conditions and what are the final conditions and solve for the appropriate one. Now, a lot of these problems, I'll give you a little hint on a lot of these problems, you're not adding or taking away gas. So that means the initial number of moles is equal to the final number of moles. And in that case, they cancel out of the equation. This is common, by the way. Not always, but this is common, that you're not adding or taking away the number of moles of gas. And in fact, this problem here doesn't say anything about adding or taking away moles of gas. So commonly, we can get rid of the Ni and the Nf. In this one, do you notice we have a sample of gas in a container? Actually, we'll just start writing down what these are. So P initial is equal to 685 millimeters of mercury. V initial is equal to 12.5 milliliters. N initial, we don't know. T initial is equal to 22.0 degrees C. P final is equal to, we don't know, that's what we're trying to find. V final is actually the same thing, 12.5 milliliters. So that means we can cross out the V initial and the V final. N final, we also don't know, but we know that it's equal to N initial. So I have no idea how much gas there is, but I know that we have not added or taken away any. And then T final is equal to 37 degrees C. Okay, so this equation gets quite a bit simpler then. I just noticed there was a mistake here. This should be T initial, not T final. So correct that, please, in your notes. So we have in this equation, what we have left is P initial over T initial is equal to P final over T final. Now, if you notice in the problem, the way it's worded, we are trying to find the new pressure. In other words, we're trying to find this final pressure. So what I encourage students to do at this point is to rearrange this equation, solving for whatever variable they are, before you start plugging things in. So I'm going to do that right now. I'm going to solve for PF. PF is equal to, and I like to also group the things together. So T final divided by T initial times P initial. That's your equation that we're going to deal with now. Okay, so from here, we just take a look at the information that we have in the problem, and we're just going to plug them in. Remember, the N's and the F's have dropped out of this equation. All we have left are the P's and the T's. So we can plug in, but not quite yet, because we do need to have things in with the correct units on them. So we need to find the pressure initial in atmospheres. So it's going to equal to 685 millimeters of mercury times 1 atmosphere per 760 millimeters of mercury. That is going to cancel that. And we are going to get 0.901 atmospheres. T initial is 22.0 degrees C. We're going to add to that 273.2 Kelvin, and that is going to give us 295.2 Kelvin. And T final is equal to 37.0 degrees C plus 273.2 Kelvin. I've added the extra decimal place because this one goes to the tenths place, so I've rounded up the 0.15 also to 2. So this is going to be 310.2 Kelvin. So now we can just plug in to our equation. P final is equal to 310.2 Kelvin divided by 295.2 Kelvin times 0.901 atmospheres, and that is going to equal to 0.947 atmospheres. Of course, depending on how the problem is worded, you might need to convert that back into millimeters of mercury. That has 3 significant figures. That's the correct answer. So you might be asking yourself at this point, well, what if I had kept the millimeters of mercury, and what if I had kept the temperature? And the millimeters of mercury you actually could have got away with. I usually like to have my classes make sure that they convert that to atmospheres just because of R, the problems we already discussed with R. But you could have gotten away with the correct answer, but you cannot get away with the correct answer if you don't convert the temperatures. Let me show you this here. So you might want to make a note to yourself. This is what not to do. So if we have P final equal to 37.0 degrees C divided by 22.0 degrees C times 0.901 atmospheres, that is going to equal to 1.52 atmospheres. You see, we do not get the same answer. And in fact, this one is incorrect. So put an X through that. So make sure that you convert the temperatures to Kelvin and do not leave them in degrees C, or you're going to get the wrong answer. If you're taking a multiple choice test, I guarantee you one of the answers is going to be 1.52 atmospheres, because I guarantee you whoever wrote that test did this calculation without converting these to temperatures. This is a capital T in the equation, which means Kelvin. You have to keep this in Kelvin in order to get the correct answer. Okay? So that summarizes changing condition problems and regular ideal gas equation type problems. Now you can go get a chance to solve some yourselves.